Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. Welcome to the first lab tutorial of 2011. So our speaker today is ΓÇ AI. ΓÇ did his PhD at the Max Planck Institute for Informatics in Saarbrücken. His thesis was about information retrieval in graph-based representations of data extracted from the web. And I think during your PhD you did an internship in MSR Redmond, I believe.
Yes, that's right.
He joined us in 2009 as a postdoc. And today he's going to tell us how to harvest and query the world's knowledge. ΓÇ.
Thank you very much, Chris, for the introduction. Actually, Chris and Tora, they both deserve a lot of credits for the talk because they encouraged me to give the talk. And also they helped me with the slides. So the talk will be about the opportunity of harvesting, structuring, and querying the knowledge on the web. And the reason why this is important is that we're facing a tremendous amount of information out there, and we need to make sense of that information. And this issue has been acknowledged by various important people in the area of information technology. So for example, the CEO of Google, Eric Schmidt, says that every 2 days now we are creating as much information as we did from the dawn of civilization up until 2003. Mitchell Kapoor, the founder of Lauder's Development, says that getting information of the internet is like taking a drink from a fire hydrant. And there are also philosophers and sociologists like John Naisbitt who say that we're drowning in information but starved for knowledge. And this is why a lot of academic and industrial projects are pursuing one vision, namely the search for knowledge instead of web pages. And the typical strategy that people pursue in this realm is a two-step strategy, where in the first step, the goal is to extract data records about entities such as people, locations, places, products, dates, etc. So we extract these data records from various web sources, and then we organize them into entity relationship-aware structures, such as this graph that you see here on the right-hand side. Now, the nodes of this graph represent entities, and the labeled edges represent facts about entities. The blue nodes stand for real-world entities or individuals, and the red nodes stand for classes of entities or so-called concepts. Now, the labels on the edges represent relationships holding between these entities, and we call such graphs knowledge graphs. And in the second step, the goal is to provide techniques for expressing knowledge queries, searching, and ranking over such structures. And the talk will be about these two steps. But before getting there, let's take a look at what I mean by knowledge queries. Here I have a few examples. So knowledge queries are queries that ask about entities and relationships holding between them. The first example asks for people who have won the same prize as Tony Hoare, who unfortunately is not here today. The second one asks for philosophers from Germany who have been influenced by William of Ockham. And the third and the fourth example ask for connections or commonalities between entities. So does anyone know the answer to this one? So what do Albert Einstein, René Zellweger, and Steve Ballmer have in common? Well, I mean, it's kind of a tough one. So it turns out that all three of them are Swiss citizens, so they have a Swiss citizenship. Steve Ballmer has an honorary Swiss citizenship. René Zellweger's father was Swiss, and Albert Einstein, he lived in Switzerland and also studied in Switzerland. And this other query is of the same type, so it's a scholarly query. In this case, it's a biomedical query, and it asks for the relation between proteins, amino acids, and glutamines. Does anyone know the answer to this one? No people with biology background here? So it turns out that amino acids are the building stones of proteins, and glutamines are one of the 20 amino acids. And so it would be really nice if we had a system that could figure out the answers to these questions. So why is it so difficult for state-of-the-art keyword-based search engines to answer these kind of questions or these kind of queries? Well, let's take a look at how Google performs on the first query that asks for people who have won the same prize as Tony Hoare. And no matter how you pose this query, Google will return plenty of results, and all of them will contain the query keywords. However, none of the results will really capture the intended meaning of the query. So what is going wrong here? Well, there are 2 points worth mentioning. The first one is that keywords are not enough to express advanced user needs about entities and relationships between them. And the second one, and maybe the more important one, is that in order to answer these queries, we need to extract information and facts from different web sources and need to combine them into unified structures, which can be used at query time. So what about question answering systems out there? They should actually do a better job at answering this kind of queries. Here I'm showing the example of TrueKnowledge, and TrueKnowledge is one of my favorite question answering systems out there. And it also follows the two-step strategy that I presented in the beginning. So it uses a suite of extractors to extract facts from various web sources. It organizes them into a knowledge base and uses it to answer user questions. In this example, we're asking who was president of US when Obama was born, and TrueKnowledge correctly gives the answer John F. Kennedy. Another example of such a question answering system is Wolfram Alpha. And Wolfram Alpha follows the same two-step strategy, although there are human evaluators who really take a look at the facts and say whether they were correctly extracted or not. Wolfram Alpha distinguishes itself from other question answering systems by performing mathematical computations on different quantities. It produces tables and plots. In this example, we're asking for the population development in China and India, and we see here that we are shown information in a structured way, information about the answer, and we are also shown the plots for the development of the population. And sometimes it may be really useful to look at the information this way. So in this example, it seems as if the reinforcement of the one-child policy in China, which happened in the beginning of 2000, really has an impact on the development of the population. Another type of question answering system is Answers.com, and Answers.com is a community-based question answering system. So the idea is that there is a repository of questions that are posed by users and answers that are provided by users from that community. So in this case, we're asking for the longest river in Germany, and we get Rhine as the correct answer. The problem with this type of question answering systems is that they cannot deal with queries that were never seen before. At least they cannot immediately deal with them. And as you might expect, these question answering systems are quite brittle. So here we are asking TrueKnowledge again for our original query. So we're asking for people who have won the same prize as Tony Hoare, and we don't get any answer. And there might be several problems at this point. So it might be that TrueKnowledge simply doesn't have the data to answer this query, or it might be that TrueKnowledge simply doesn't understand the query. And so I did some further investigation, and it turns out that TrueKnowledge has the data to at least partially answer this query. So it knows about prizes won by Tony Hoare and Leonard Edelman, for example, and so it could provide us with an answer. But no matter how I pose this query, it really doesn't find any answer to it. And so this lets me think that it really has a problem understanding it. And this is really the brittleness of such systems, so you need to be very careful about the way you write your question. Here is another system. This is the Yago-Naga system, which I've been working on during my PhD thesis. And the Yago-Naga system also follows a two-step strategy. So we extract facts from various web sources, we combine them into a knowledge base and use them to answer user queries. The Yago-Naga system provides a graph-based query language to express knowledge queries. And for the very same query that asks for people who have won the same prize as Tony Hoare, we get Herbert Simon and Marvin Minsky, two of the founding fathers of AI, in the top 2 positions, followed by other prominent computer scientists. And so this hints at another question, namely, how do we rank answers about entities and relationships? And I'm going to give an answer to this in the course of the talk. In terms of research in this direction, there is research that comes from 3 main areas. The first one is information extraction and ontology construction, and prominent projects here are DBpedia, Yago, the Linking Open Data Project, and Freebase. Freebase was recently acquired by Google. There is the area of entity search and question answering, where we have systems like EntityRank. This is the theoretical framework behind EntityCube, which is one of Microsoft's products. Then there are systems like TrueKnowledge and Wolfram Alpha I just presented, and there is also PowerSet, which was acquired a few years ago by Microsoft. Then we have the area of graph-based information retrieval, and there we have graph-based query languages such as Sparkle, the query language for RDF data. We have the Nagas system, we have XQuery full text, we have conjunctive data log, and many more. And I'm going to talk about some of this in the talk. Now, as depicted by this figure here, the boundaries between these areas are kind of blurred, and there is wide intersection between them. So for example, the efforts by the semantic web community lie somewhere in the intersection between these areas. Now, one question that arises is whether all these efforts that we just saw are in vain. And one good reason to ask this question is that we have been dealing with such systems in the past, namely in the 80s and in the 90s, in the context of expert systems. And expert systems are rule-based systems which operate on the knowledge extracted from a certain domain. So the idea is to have automated systems that replace the human experts from that domain. And people very soon encountered various problems with such systems. I've listed some of the most important ones here. So it turned out that it was very difficult to maintain knowledge as it evolved, and the systems were very brittle, so depending on the user input, sometimes the rules would fire and sometimes they wouldn't. And historically, there has always been a disagreement about the way knowledge is represented and the level at which it is represented. And these rules involve complex reasoning, which usually leads to impractical computation times. And there has also been a dispute which has encompassed various academic communities, and it's best captured by the dispute between Marvin Minsky, one of the founding fathers of AI, and Hubert Dreyfus, who is a phenomenologist, so a philosopher basically. And Marvin Minsky's goal was to apply the theory of Thomas Kuhn about paradigm shifts to the theory of the mind. And in a seminal paper of 1975, he proposes the frame systems as a framework for representing the most basic constructs of thought. And the idea behind the frame systems is really the basic idea that underlies most of the well-known knowledge representation formalisms that we're using nowadays. I don't want to go into details here because I'm going to discuss some of these formalisms in the next slides. But the basic idea is to organize knowledge in subclass hierarchies where all classes have terminal nodes, and these terminal nodes are basically placeholders for individuals or real-world entities. And these terminals may be shared across different classes. Hubert Dreyfus was a little bit skeptical about Minsky's ideas, and he says, quote, that there are hints in the frame paper that Minsky has embarked on the same misguided infinite tasks that eventually overwhelmed Edmund Husserl. And he goes on by saying that Minsky's naivety and faith are astonishing. Philosophers from Plato to Husserl who uncovered all of these problems and more have carried on serious research in this area for 2,000 years without notable success. And although the arguments by Dreyfus seem to be subjective in nature, history has given him right, so far at least. So the question that we have to answer is there another opportunity? And I believe that there is another opportunity, and at least this is what I've argued for in my thesis. And actually, if we look at the efforts that are being made in the area of semantic web, so the semantic web is the term that I use for that part of the web where people are putting manual effort to assemble ontologies and thesauri, such as WordNet, Sumo, Psych. These are some well-known thesauri out there. And if we look at the efforts that are being made in the area of social web, this is that part of the web where people are manually annotating information, they are giving structure to the information, they are interlinking it. So these are platforms such as Wikipedia in the spirit of Web 2.0, Facebook, IMDb, DBLP, etc. Now if we extract information from these two web sources and combine it, then this might lead to an improvement of our information extraction techniques. So we might come up with lightweight information extraction techniques that can scale at the scale of the web. And this, again, might give incentives for more flexible and pragmatic knowledge representation techniques, which can be easily updated and do not involve complex reasoning. And so really the bottom line here is that while some of the early AI projects were really based on idealism, some of the most successful semantic web projects, as we will see in the next slides, are purely based on pragmatism. In the next part of the talk, I will present some of the knowledge representation and reasoning mechanisms that are well known nowadays, and then I'll talk about a new methodology for performing large-scale information extraction by combining semantic web and social web sources, and then I'll talk about some of the query languages that we use for these knowledge graphs, and then I'll discuss the issue of ranking. For a long time, the state of the art for representing information on the web has been through natural language text, structured or formatted through HTML tags. And actually, we know that this is only half of the truth because there are also fancy technologies out there, such as Ajax, JavaScript, and JSON for presenting this information in a more dynamic way. But recently, people have started thinking about more explicit ways of representing information, namely representing the knowledge that is contained in that information. And this is through entity relationship kind of graphs. So, for example, the scientist Sam Smart graduated from the University of Cambridge would be represented through this entity relationship graph. So we have the scientist Sam Smart, who is of type scientist, who graduated from the University of Cambridge, and who has a certain name, which is Sam Smart in this case. And the advantages here is that we have a specific structure, and actually if we know some properties of these relationships and entities that we have here, we can also perform logical reasoning over these structures. And this kind of structures are the basis for formalism such as HTML5, which contains RDFA, microformats, microdata, and many more. And the goals here are to standardize the description of knowledge so that knowledge can be shared across various domains and across various systems. And one of the main goals, of course, is to enable query answering at entity and relationship level. Now, the most well-known knowledge representation formalism that is provided by the semantic web community is the Resource Description Framework Schema, or RDFS for short. And RDFS enables the representation of knowledge from a certain domain through entity relationship entity triples, or which have the grammatical form subject, predicate, object. So if we want to express the Sam Smart lives in Cambridge, we construct this triple which has a subject, a predicate, or a relationship, and an object. And this triple is called a statement in RDFS, and all these elements that I just introduced are resources, are RDFS resources. Now, it seems to be pretty straightforward to represent binary relationships, but the world is slightly more complex, so sometimes we need to also talk about n-ary relationships. So in this case, we might want to express that Sam Smart lives in Cambridge in 2011. And the mechanism that RDFS provides to express such n-ary relationships is the mechanism of reification, where the idea is to reduce these n-ary relationships to binary relationships. I'm going to show this by means of an example. So we know how to represent this first part. We just saw it on the previous slide. It's basically a triple. So now we want to say that this triple holds in 2011. And so what we do is that we introduce an ID for this triple, in this case, living 42. We say that this triple, or this ID, has a subject, which is Sam Smart. It has a predicate, which is lives in, and it has an object, which is Cambridge. We say that it's an RDF statement, and now we can start talking about it. So all we need to do is to introduce a new relationship and say that it holds in 2011. So this is all that there is about reification. Another nice thing about RDFS is that it comes with decent reasoning capabilities. So we can do reasoning over the types of entities. We can do reasoning over relationships and over the properties of relationships, such as transitivity. And I don't want to go into details here. You don't need to understand all of them. But if you take a look at the first rule here, what it says is that if entity X is of type Y and entity Y is a subclass of Z, then we can deduce that entity X is also of type Z. So X, Y, and Z in this example are variables, and if we want the rule to fire, we have to replace X, Y, and Z with entities from the underlying knowledge base. So for example, we could replace X with Albert Einstein, Y with physicist, and Z with scientist. And what the rule tells now is that we can deduce this new fact here, that Albert Einstein is of type scientist. If we want to go for more expressive reasoning, or for more powerful reasoning, then we can use the web ontology language, or OWL, which is an extension of RDFS. And OWL provides an extended vocabulary for defining set operations on classes as well as restrictions on classes and properties. So for example, one could say that the born-on-date relationship is a functional property. Now, a functional property is an n-to-1 relationship, which means that many people can have the same birth date, but for a person there can be only one birth date. And this is some kind of restriction on this relationship. But we can also define set operations such as disjoint with. So in this case, we are expressing that blood type A and blood type B are disjoint. And these are just some examples, but there are a lot more possibilities to express such restrictions and operations. And OWL is very powerful. It deals with the principle of reification. One can deal with classes in the very same way one can deal with instances or with individuals. And it also introduces this new concept of blank nodes. These are unknown entities. And so reasoning is very powerful in OWL, and it's so powerful that OWL itself is undecidable. More specifically, the satisfiability problem, whether there exists an individual to a given class, this is undecidable. And this is why OWL comes with two restricted subsets, OWL-DL, which has the same expressive power as description logic, and a more restricted subset, OWL-Lite. But really the most practical formalism here that is being used nowadays is RDFS. Now that we know how to represent knowledge, let's take a look at how we can populate our knowledge bases. Here we have the Wikipedia article about Albert Einstein, and we see that it contains many interesting facts about Albert Einstein. So for example, it contains the birth and death date. It contains facts about his profession, as well as about his scientific discoveries or results and collaborations. And in fact, we could try to extract such facts by using various information extraction techniques such as natural language processing, pattern matching, statistical learning, and many more. But there are some problems with these techniques. So the first problem is that often the extracted facts have a very low confidence. So often the confidence is significantly lower than 1. Actually, there is nothing wrong with this because we could still deal with these facts in probabilistic databases or in databases that can handle uncertainty. But the second problem is that these methods also involve high computational costs. And so if we want to go for large-scale knowledge bases that contain the knowledge of the web, we need to think about other ways. However, there are systems such as Rascally, which is a German-Austrian project, that are using exactly the statistical information extraction techniques to extract information from the web. And Rascally uses these techniques to construct social networks where the facts are extracted from yellow press pages, blogs, and gossip sites. It provides a fancy user interface where the user can enter his question in natural language. The results of the question are shown in a structured way, and there is an avatar who from time to time talks to the user. And so Rascally applies its information extraction techniques to these very reliable pages that you see here, and it can extract facts about Madonna. So for example, it can extract the fact that Madonna was married to Guy Ritchie and that she had Vanilla Ice as a boyfriend. And similarly, it can extract facts about all other boyfriends and girlfriends of Madonna. And in this, so this seems to get pretty wild here, but I think this is a nice example where information extraction techniques can be used without caring too much about the accuracy of the techniques. Some of the really successful projects out there for constructing knowledge bases have tried to, they basically go for the low-hanging fruits out there. And these are Web 2.0 kind of sources such as, or platforms such as Wikipedia, Facebook, IMDb, DPLP, etc. And here I'm showing, so the reason to go for these platforms is that they provide information in a kind of semi-structured way. So here I'm showing the example of Wikipedia. Here we have the info box about Albert Einstein. If we look here, we have a lot of interesting facts. So we have the birth date, the death date, the citizenship, etc. And this simplifies our information extraction techniques because now we don't need to deal with statistical techniques anymore. All we need to do is to write our regular expression matchers and extract the facts from these assets. And these info boxes that you see here, they are predefined for various classes. So for example, there is an info box for scientists, for artists, for products, etc. And assets of the same kind are the categories of Wikipedia. So here we see the categories of Albert Einstein. And again, we see interesting facts. So here we find his birth year and death year. We see that he belongs to the class humanist, philosopher, and physicist, and cosmologist. But we have to be careful here because he is also in the category Einstein family and ETH Zurich faculty, but he is neither a family nor a faculty. Similar asset are the Wikipedia lists. So here we have a list about Nobel laureates in physics. And all these assets actually simplify our information extraction techniques a lot. Now, one other thing that I should note here is that the classes that are provided by Wikipedia, they are kind of structured in an ad hoc way. So Wikipedia has a lot of information about individuals, but doesn't know much about the classes to which they belong. On the other hand, semantic web sources such as WordNet, Sumo, Psych, etc., they have a lot of information about classes. So they actually provide taxonomies of classes with hundreds of thousands of classes and the relationships between them. So for example, Wikipedia has a taxonomy of hundreds of thousands of classes and structures them in a class-subclass hierarchy. So here I'm showing the example of the class scientist, and we see here some of the direct hyponyms or direct subclasses. So for example, a physicist is a scientist. And the problem of these sources, though, is that when it comes to individuals, they know for every class, they know only a handful of individuals. And so the idea that comes to mind here is, can we maybe combine the information that these sources contain about the classes with information that sources such as Wikipedia contain about the individuals? And this is what we did in the project Cointiago. There we took the facts that WordNet has and combined them with facts that we extracted from Wikipedia. And this gave us a large-scale knowledge base, which is Yago, and Yago is one of the largest knowledge bases that are freely available out there. Its first version had around 30 million facts, and right now we have 160 million facts. The only largest knowledge base is DBpedia, but the accuracy of DBpedia is unknown, whereas the accuracy of Yago is 95%, and this is pretty high for this kind of automatically constructed knowledge bases. And the way we evaluated the accuracy was by means of careful sampling. So for each of the relationships known to Iago, we sampled some facts, and we showed them to users along with the corresponding Wikipedia pages. And so the users had to say whether the facts were accurate or not with respect to the Wikipedia page. And both Iago and Wikipedia have been integrated into the Linking Open Data project, which is a major effort by the semantic web community to bring all these RDF data sources together. So this is a semantic ecosystem that can be used by various companies to provide to deal with semantic tasks. And some of the companies are using these sources that you see here to provide search at entity and relationship level. Now the role of Iago in this Linking Open Data project is that it provides the semantic backbone or the taxonomic backbone of Wikipedia, because it provides the links to the WordNet classes. And they may be really useful for reasoning tasks. Now let's take a look.
So what data can we get
From ACM? So I don't know exactly, but probably about publications, data about publications, authors, and
it's actually sort of XML IDF format as opposed to web pages.
I think it's XML, but I'm not quite sure. I'd have to check this. Right. But the sources that you see here, they are all compiled in RDF, right? So here you'd get RDF text, which is basically XML. So right. Now let's take a look at the query languages that we can use for this kind of knowledge graphs. Now, if we take a look at our original query, it's so basically that asks for scientists who have won the same prize as Tony Hoare. Its logical representation is this one, and it's a conjunction of predicates, as you see here. So we have an existential quantifier of the variables x and y. We're interested in the variable x. X should be of type scientist, y should be of type prize, and Tony Hoare should have won that prize, and that other scientist should have won the same prize. Now we can go from this logical representation directly to a conjunctive data log query by basically replacing these conjunctions through commas and omitting this existential quantifier. And we still need to say that we are interested in the variable x. And now we have, again, the very same predicates. And now all that we need to do is to replace these variables that you see here with entities from the underlying knowledge graph. And so we basically need to find triples that satisfy these patterns that you see here. Another well-known query in the semantic web community, for the semantic web community, is the Sparkle language. So this is the language for RDF data. And Sparkle is an acronym. It's a recursive acronym that stands for Sparkle Protocol and RDF Query Language. Sparkle is very similar to SQL. And each of the rows that you see here represents one of these predicates in the same order. And these are the so-called Sparkle patterns. And in order to answer this query, we need to find edges in our knowledge graph that satisfy these patterns. Sparkle also provides a preamble, and in this preamble we can write prefixes. These prefixes are shortcuts to other repositories out there. So for example, here we have a shortcut RDF, which allows us to access the vocabulary of the RDFS repository. And here we have another shortcut, which may be a shortcut to some example knowledge base. And now we can access the relationships and the entities of those knowledge bases, and we can construct our query. Another system that provides graph-based search is Naga. Naga is an acronym that stands for Not Another Google Answer. And Naga is a general framework for expressing queries about entities and relationships, for providing graph search at entity and relationship level, and for providing ranking at entity and relationship level. So Naga's query language is graph-based, so every Naga query is a graph, and the nodes can be labeled with entity names, and the edges can be labeled with relationship names, and actually both nodes and edges can be labeled with variables. So if you look at this example that asks for prizes won by people who stand in any relationship to Max Planck, $X, $Y, and $I are stand for for variables. Now, in order to answer such queries, we need to find, again, a subgraph in our knowledge base that matches the structure of the query, and as well as the labels, and binds the variables through entities and relationships from the underlying knowledge graph. Now, up to this point, Nagas query language was very similar to the languages that we just saw before, but it goes beyond them by allowing the definition of regular expressions over relationships on the query edges. So, for example, if we were asking for a philosopher from Germany who has been influenced by William of Ockham, this relationship from is kind of a vague relationship. And if we want to express that, we can say that this philosopher, he might have been born in, he might live in, he might be a citizen of some place that is located somewhere in Germany. And here we can use the clean star to capture the transitivity of the located in relationship or of the influences relationship. And similarly, we can use the wildcard here to ask for unknown relations or for connections between entities such as Steve Ballmer, René Zellweger, and Albert Einstein.
Question?
Yes?
The dot star, does that mean sequence of edges between them?
Exactly.
Or is that one?
No, it's a sequence of edges. So any path that interconnects them.
And it's, you're not constraining it to be the same.
No. There is no constraint here. So it's just find me any path that. What?
That's not necessarily a very good representation of that question, because that question says what do they
Right. So this is just the syntax of this query. I could have done it also differently. I could have just have a star connection here between these three. Just a syntax. Actually, when you write it in the query interface, you just say connect these three entities, and you might find a tree that interconnects them or various paths that interconnect them. You know, so it just, I guess it's just this is just a syntax. It doesn't say anything about the semantics. The semantics is really here in the query. Just find anything that these three entities have in common. Now, as I already mentioned, in order to find the results of such a query, we have to apply subgraph matching algorithms. And for a given graph query, there may be multiple subgraphs that match it. And so we need to think about ranking. And we identified some ranking criteria for our system. The first one is the confidence, which means that we prefer results in which the facts are likely to be correct. And this comes with two subdimensions. The first subdimension is that the facts should come with high extraction certainty, and the second one says that they should come from high authority sources, because it really makes a difference whether we extract our information from some obscure page or from a reliable page. Another criterion is the informativeness, and what it says is that we prefer results that are likely to be important, and one way to capture the importance of facts is by looking at their frequency in the underlying corpus. For us, this corpus is the web. So I'm showing here again an example. If we want to know what Albert Einstein is known for, we would prefer, for example, that he is more known for being a physicist than a vegetarian. On the other hand, if we want to know people who are vegetarians, we would prefer Albert Einstein to rank higher than some unknown person who happens to be a vegetarian. And then the third criterion is the compactness, which says that we prefer results in which the query entities are tightly interconnected. So for example, if we ask for a connection between Albert Einstein and Niels Bohr, we prefer their connection through the Nobel Prize to their connection through Tom Cruise, who is a vegetarian as Albert Einstein was, and who happens to be born in the same year in which Niels Bohr died. I wanted to show a short demo of the Nagas system. So there is online, there is a web interface. So here, if you see, I just ran this query previously. So if you see, I ran the query about the connection between Albert Einstein, René Zellweger, and Steve Ballmer. And here you see that all three of them are Swiss Americans. And actually, if you check it on Wikipedia, then you also find the reason for this. So let's start with a simple query and have a look at the ranking. So let's say we are interested in what Albert Einstein is known for, to know all the classes Albert Einstein belongs to. And we can use a regular expression. Type subclass of. And as you see here, let me just put a star there so that we get all classes, not just the direct classes, or in two steps. So you see here that we start by getting the most prominent classes he belongs to, such as physicist, theoretical physicist, ETH Zurich alumni, etc. And then we get, like if we go further down, we get more general concepts. Let me go further down, like scholar and. So ranking is really important here because we could get like really general classes such as person, which are kind of obvious, and we want to avoid that. On the other hand, if we ask for well-known physicists, so we could ask, for example, people who are known for being physicists. Then we again want to get the important physicists first. And here we see that we get Albert Einstein, Max Born, Joseph von Fraunhofer, Max Planck, and other important physicists. So this just gives an idea of how the ranking kind of works. And you can also ask for connect queries. So for example, we could ask for oops. So this underscore notation, this is a convention that we use to refer to the entities in the knowledge base. If we don't know the name of that entity exactly, we can use also quotes for the name, and then this string will refer then to that entity. So for example, we can say Tom Cruise. So this is just a tag that refers to the entity Tom Cruise, or might refer to the entity Tom Cruise, we just don't know it. And let's say Max Planck. Now these are really difficult queries because here we're asking, for those of you who know the theoretical problem behind that, this is the Steiner tree problem, and it's a really difficult problem. So it's NP hard, and here we have a very efficient algorithm for solving this kind of task. And here you will see, for example, that, so if you look at the first row of the result, it says that Tom Cruise means Tom Cruise. And this is a simple example, but there may be more complex examples. And we see, for example, that Albert Einstein and Tom Cruise are vegetarians, and so on. And it might turn out that we find really interesting information about these people that we have here. Right, so if you want, you can try it out yourselves. It's online, and if you have the Java runtime environment installed on your machines, then you can actually browse the knowledge graph. So here you see that we have here the knowledge graph, and you can actually click on the nodes, and you can go from node to node and get a feeling about the data that we have in our knowledge base. You can all try it out yourself. It's out there. Now let's see. Okay, so I'm almost done. So we started out with a vision of constructing web-scale knowledge bases with efficient and expressive search and ranking capabilities. And nowadays we have lots of systems that actually provide these search capabilities over hundreds of millions of triples extracted from various web sources. Now scaling this for the web is still a challenge, but I think it's an exciting challenge that should appeal to and benefit from various communities such as databases, information retrieval and extraction, social and semantic web, machine learning, and many more. And I hope that I could convince you that by combining knowledge and inference with expressive search and ranking capabilities, we can go a long way and hopefully to a more knowledgeable web for the future. Thank you. I know.
This seems like super critical, right? Do we have anything within Microsoft that kind of?
Yes, so there is an effort by people in Redmond. They are working on a Satori knowledge base, which basically tries to combine facts about products and individuals out there in the web. They're working on representation formalisms as well as on extraction techniques, basically. And we've also been talking to them, so.
So I guess a key challenge is incorporating uncertainty and doing probabilistic reasoning over these graphs, which you're working on this.
Exactly. So I've been working on this for the last 1 year or so that I've been here. Yeah, and that's very challenging because reasoning over such graphs, these are very large graphs, and reasoning over them can be very complex.
Do you want to hazard a guess as to where we'll get to in the next 3 or 4 years with that?
So right now, people from the semantic web community, they haven't thought so much about probabilities for these triples that they have. But I think in the coming years, this will become really important, and people will start thinking about these issues. So but it's hard to say whether reasoning will be efficient or people will deal with this type of reasoning efficiently in the next years. It's hard to say. Yes?
So you talked about the extraction uncertainty associated with a particular relationship that has been extracted from the web.
Mhm.
But all the sort of facts were objective questions about whether a person is a scientist or not.
Right.
But I saw a relationship, Albert Einstein is a comedian, and it was mentioned that there's a 20% accuracy of. So what about answering questions which are more subjective in nature? When somebody asks online, what is a good Italian restaurant in Cambridge? Now it's people specific because there is no objective answer to that. So like different people might prefer different sort of restaurant, and then there's also the question of whether the reliability of the source from where the fact was extracted.
Right.
So has there been any work on distinguishing between these two sources of variation in the fact?
So, to the best of my projects such as Yago and Wikipedia that I just presented, they try to not deal with this kind of subjective facts. To the best of my knowledge, projects that want to capture subjective nature of questions, these are typically projects that use the wisdom of the crowds, you know, so for this kind of knowledge bases, it's not an issue yet, because as I said, people are not dealing with probabilities, people are not trying to aggregate opinions about these queries. We've been looking in the last year into this issue, but yeah, so this is what people have done so far.
Question? So you listed a bunch of problems that all systems have, which seem to be very much the same problems you run into in systems as well. For example, maintaining knowledge over time would seem to be a big issue here as well.
Right.
For example, if someone was a vegetarian on and off every other year, right? I mean, you said you have this assertion Tom Cruise is a vegetarian, but should they?
Right.
Albert Einstein was a vegetarian, but shouldn't these be sort of conditioned on various different things?
No, absolutely. So now extracting this temporal information is still an issue, and it can be quite difficult. But the representation formalisms, as I showed with reification, they allow you to represent this kind of thing. So you can say that somebody was a vegetarian starting from that year to that year, from that month to that month. So you can represent these things, but now the information extraction techniques still cannot get this fact. So this is the main problem. In terms of updates of the representation formalism, the representation formalisms are quite pragmatic, and they can be easily updated. The ones that I presented here, so RDFS, for example.
You mean updated with new facts?
With new facts, right?
There's another type of update, which is the fact that's changed,
Right,
right?
right. But right, this is just a fact about that fact. So actually, that fact has an ID now, and you can talk about the ID. This is the principle of reification that I just. So the update is there simple as well. It's just adding a new triple to your knowledge base.
Well, this is the thing I don't get, because when you put all these wildcards in, you'll get all that stuff, right? Presumably. So if I have these two contradictory facts, which hold in different periods of time, and I put all these wildcards into my queries, I'm just going to get both of them, right? Or what am I going to get?
Well, the idea is right. You'll get the base fact, but then that he's a vegetarian. But then you'll get also temporal information about that fact, right?
But my example was suppose the fact and the negation of the fact both hold at different times.
Oh, we don't have negations of facts here in this kind of
No, what
representation.
I mean is he's something other than a vegetarian, right?
Okay.
I was a vegetarian last year, and I'm not a vegetarian this year. And both of those facts can be in the database, right?
Right.
I assume.
Right.
And
But
now if I do a query, what am I? What comes back?
you'll get the information with a temporal assignment, right? You are not.
So you get both.
Yeah, you get both.
So essentially what happens is as information gets updated, it just concatenates into a larger and larger database.
Right.
And all of these facts can come back.
Right, but then it's a question of ranking again, right? So are you more well known for being a vegetarian or for being a non-vegetarian, right? So the idea is to have the information about every individual out there with respect to each time point. This would be the basic idea.
So where does this well-known thing come from?
RDFS? Or?
Would I be well-known? Is well-known a triple in the database? Or?
No, this is importance. This is the informativeness aspect that I just represented. Oh, it's how it's computed or represented? Well, by a score, basically, in our model. So it's just a score. It's a ranking score with respect to that.
You're saying each triple has this number associated with it.
Right.
And where do these numbers come from?
Oh, these are basically the values that you compute for each of these aspects that I introduced here. So this here. So this criteria actually introduce weights for each of these dimensions, and this is what we have done in our system. So if you try out the Naga engine, you'll see that every result has a score, and this is the combination aggregation of these three aspects that you see here.
Well, okay, my question is, you've reified the relation and then made a connection that says this has importance 0.5.
No. So the Yago model is a little bit different from the simple RDFS model. So we don't have a triple store, we have a quadruple store if you wish. So we have also a fourth column in the table that just has this value, this aggregated value.
Any other questions?
Coming back to Tom's question, you have a fact like that somebody is a vegetarian, and it's sort of a temporal fact, right? It might change.
Mhm.
So there are two ways of resolving it. In the future, what you can change the definition of the fact by saying this person, Tom Cruise, at some point in his life was a vegetarian.
Right.
It becomes a more relaxed fact, right? And then it's obviously
Right.
and even one instance was good. If he was a vegetarian in 2001, it was fine. The other thing which relates to my first question is on the question of conditionality. You can say that if you see that there is a fact and there is a high uncertainty about a particular fact, about a particular relationship, then you can sort of condition it on, say, the perspective of a person, right? You can say, according to people in Cambridge, which restaurant is the best
Right.
restaurant, and then probably the certainty is of 4. Or you can condition it on other variables, not like from where the fact was extracted, but what is the time stamp associated with that? What
Right.
is extracted in 2001? So in 2001, Tom Cruise was a vegetarian, say. So you will get higher certainty that Tom Cruise was a vegetarian, but in 2003, he was a non-vegetarian.
Right.
Right, so it's about adding conditionality to the facts over time by introducing new variables,
Right.
introducing new parameters. So as any sort of framework, this sort of framework sort of allows that to the introduction of new parameters in relationships
Mhm.
to make sure that the certainty can be improved.
So as I said, if you want to add a new fact about a known triple, you can do it with the current frameworks. Now, if you want to add probabilities about that new triple, the current frameworks do not allow that. But such a framework such as Yago, it allows you to add these probabilities about the new triples that you add to the store. So to the best of my knowledge, Yago is that framework that allows you to add probabilities and still use reification. And it's still a very pragmatic framework, so it doesn't involve any complex reasoning or so.
Any last questions? Not where it was slightly early, but hopefully there's a glass of wine and some nibbles outside. I think it's an incredibly ambitious research area, but I guess if we can make 10% of the way towards the goal, it will have a huge impact. So let's thank Jerry for a lovely tutorial.